Okay, yesterday we talked about what a discrete event simulation is, and we gave one example, which was kind of the simplest one. So today I'm going to give a slightly more complex example, and then we're going to be the event list. We're going to perform a simulation by hand. One of the things that I mentioned is that these simulation models, as we are going to be talking about them, by defining them in terms of parameters, states, state transitions, and events, that is in every sense of the word a simulation model. And we're going to prove that by actually simulating it by hand. Okay, so that's going to be a bit tedious. And so since it's very tedious, I will do it, and then I will ask you to do it. Not here, but in the first assignment. Our first Hello World model was that arrival process in which we're just modeling things that kind of show up. One of the use cases of that, one of the most common applications of that type of thing, is a situation in which customers, and I'm putting customers in quote, because this can model things where the customers may not necessarily be literal customers. But these customers arrive to a facility one at a time, and there are a certain number of identical servers, again, servers in quotes. And the idea is that if all the servers are busy, then the arriving customers wait in a queue. When the server completes service, then that server they, meaning the server, starts on the next available customer if there are any. The idea here is that when a server is serving a customer, then they can't serve any other customer. The server can only serve one customer at a time. And so here's how that might look if the number of servers is 3, for example. So here we have, here we have 3 servers, 1, 2, and 3. Notice that they're listed as being roughly identical and kind of anonymous. So in this model, all the servers are basically identical. Then we have all of it. These are our arriving customers, and these are the customers who are waiting for somebody to complete. Oops. These are the customers that are in service, and then these are the ones that have left. So this should provide roughly a picture of what's going on. And if you've ever been to a bank or a ticket counter or virtually almost anything else, you will have encountered a situation like this. Okay, so is it clear what we're modeling? We're going to start with the simplest one, in which case we're going to assume that there's just one server. So that's okay, multiple server model. So here's, but first let's create the model. Remember, we have parameters, we have state variables, and then we have our events, which are based on the state transitions and the relationship between them. Okay, so the first parameter are these inter-arrival times. That is, those are the times between when these people show up. So that would be roughly the amount of time there. Once they show up, they're kind of stuck in the line. Our second parameter is going to be a set of service times. That's how long it's going to take. So when you show up to the server, that's going to be how long it takes for them to process your order or your transaction, whatever that is. Okay, so that's different than the inter-arrival times. And that's going to typically be some function of how fast the servers work and how much work you have to do. If you think, one image you might have, and that this doesn't exactly fit the multiple server, but think of a supermarket where there's only one checkout person. And so everybody has to wait on one line. And each person has different numbers of items in their basket. So roughly how long will it take to process each customer? Well, that's going to be some function of how many items you have. If you have, say, 3 items, it's going to be relatively short. If you have 20 items, it's going to be presumably proportionally longer. So we're not going to model things like that, although we could. But for this model, we're just going to say, well, the service times are typically going to be some random quantity based on a particular distribution. The third parameter is going to be the number of servers. So for this model, K is equal to 3. That is, there are 3 servers. The assumption of this model is that that number isn't going to change. So for this model, there are going to be 3 once and for all, and that's it. Those are the quantities that don't change. The state variables are the ones that do change. And we're going to focus on 2 state variables, Q and S, and then a third, which is a derivation of them. So our first state variable is going to be the number in the queue. So here, this guy hasn't quite arrived. So in this particular case, Q is equal to 3. Right here, okay. Our second state variable are going to be the number of available servers. And in this case, okay, the number of available servers as opposed to the total number we have. In this particular case, the number of available servers is 0 because they're all busy. Okay. The number in parentheses is the initial value when we start our simulation. And that's something that's always required when you define a simulation, one of these simulation models. So this says when we start off, there are going to be no customers in the queue. And when we start off, all our servers are going to be available. So there will, at the very beginning of the simulation, there will be K available servers and 0 in the queue. Now, one of the other items that we might be interested in is the total number in the system. So, and by the system, in this case, it means this, the queue and the server. So it doesn't count the customers who haven't arrived. It doesn't count the customers who have already left. It just counts the number of customers in the system. In this particular case, the value of L is equal to 6. And we can do that just by counting the little guys here. But we can apply this formula, which is always going to be the case. That is, the total number in the system is going to be the number in the queue plus the number who are in service. And that's going to be the total number of servers minus the number of available servers. So if we look at that, Q is 3, K is 3, and S is 0. And so we get 6. So we could define our an additional state variable. In the case of, in the interest of simplicity, though, we don't really need to, because if you tell me Q and S and I know K, then I'll be able to tell you L at any point in time. So that's something that we don't necessarily have to do. Okay, so now let's define our model, our state transition. So first, we always have a run event. And the run event always sets the state variables to these initial values. So in this case, Q is 0, S is K. And so the state transition of the run event sets Q equal to 0 and S equal K. We can read that right from our definition of the state variables. And like the arrival process, we're going to schedule the first arrival with a delay of T sub A. Now remember, T sub A is the first inter-arrival time. One thing to note is, notice the difference between defining this sequence with the curly braces, which indicates that it is going to be a sequence, versus using it just as a scalar, which says we just grab the next one. Okay, so that's the run event. We're going to define an arrival event. And what does an arrival event do? What we're going to do is we're going to say just a customer that arrives, we're going to put them in the queue. What does that mean in terms of the model? That says that when a customer arrives, Q is equal to Q plus 1. That is, the number of customers in the queue is one more than it was right before when that happened. So looking at this, this guy's just about to arrive. And if that's the next event that occurs, then Q is going to go from 3 to 4 in that case. Now, in terms of scheduling, what we're going to do is we're going to say, well, all right, they've gone into the queue, but they could go into service immediately. So if a server is available, then we're going to schedule to start service with a delay of 0. Again, think of what would happen if you show up to the bank. Again, typically they have these little velvet ropes that create a single queue, a single line. And you come into that line, and then you notice that there is a teller available, and then you immediately go to them. So in this model, we're going to assume that that delay is 0. That it takes you 0 time to get from the queue to the teller or the server. But we can only do that if a server is available. That is, if you show up at the queue, even if you're the first one and you notice that there's a customer at each of the servers, then you can't go there. What is the model criterion? The model criterion is that if there's an available server, then we're going to schedule an event we're going to call start service with a delay of 0. And then furthermore, the way the model is going to work is like the arrival process, we're going to schedule the next guy after another delay of T sub A. So in this case, the arrival event schedules 2 events. So when this guy, like if that's the next one, if this guy shows up and now Q is equal to 4, then the time between when he shows up and the next one will be another T sub A. So one thing to understand and just sort of keep in your mind is that the times in discrete event simulation are always relative. They are typically the time from now until some event in the future. Okay, so we schedule another arrival after the delay of T sub A. So basically this is, we have this arrival process is kind of embedded into this model. Okay, so, but wait, there's more. So what about that start service event? What is that going to do? Well, what the start service event does, one of 2 things. It actually, it does 2 of 2 things. First of all, we take somebody out of the queue, and then we take a server out of the available pool. So the start service event is going to decrease Q by 1, and it's going to decrease S by 1. In other words, we take a guy out of the queue and we take a server out of the available servers. Okay, so that's why, because once a server is serving 1 customer, that's all they can do until they're finished with them. Once a customer goes into service, they're not in the queue anymore. And so the queue goes down by 1. And once they start service, we're going to schedule an end service event with a delay of our T sub S. Now, what was T sub S? That was our service time. So that says is that when I start service, I'm going to finish after this amount of time. So one important thing to recognize from this is that the way that this model is constructed, each event has just one job. And that's kind of an ideal that you want. You don't want events that try to do too many things. So just as the arrival event has one job, and that's to put a customer in the queue in terms of the state transition, and as part of its job to possibly schedule the start service and to always schedule the next guy. The start service event, what's its job? Its job is to take a guy out of the queue, take a server out of the available servers, and then schedule when they're going to complete. But that's it. And when you say schedule that, all that's doing is that's putting an event called end service on the event list. We'll see what's going on with that. And finally, the end service event. Now, what does that do? That means that this customer has finished service and leaves. So that's what's happening. That's what's just kind of happening here. Like this guy left a while ago. This guy left in between. This guy just left here. So a short while ago, this customer had an end service event. They left the system, and we don't care about them. I know that sounds harsh, but as far as the system is concerned, we're basically done with them. So the end service event, now that customer is left, we now have the servers available. And so now, in terms of the model, we have one more server than we had before. Okay, but what's that server supposed to do? That server is supposed to serve another customer if there's one available, if there's one waiting. How do we know whether somebody is in the queue? Well, we have the state variable, queue, and if that's bigger than 0, that means that somebody is waiting in the queue. And we're going to schedule another start service with a delay of 0. Again, we're in this model, remember all models are wrong. You say, well, it's going to take maybe a second or two to get from the queue to the server. We're just going to ignore that and say it takes 0 time. That's what this model does. Okay, now when after we've finished with the model and maybe executed it for a bit, and as we would for when we were actually implementing this, we would take a look at some of these assumptions and say, is that really going to be influencing our the measures of performance or measures of effectiveness that we're looking at? Okay, but for right now, this is our model. So we have 3 parameters, 2 state variables. This is a derived state. The L is a derived state variable. So we have 3 parameters, 2 state variables, and then 3 events plus run. You always have the run, so that doesn't always count. So we have arrival, start service, and end service. Those are the 3 things that happen, and the 3 ways in which we our states can change. Okay, so now
Sir,
we
I got
have
a
the
question.
model, and we can declare victory and go home, except that we need to actually be running the model. Now, in actuality, at this point, we would be implementing it on the computer. Now, after tomorrow, we would actually be reformulating this using something called an event graph that we'll talk about then. But for right now, we have our model in place. And now let's see what happens if we try to execute that model. Just a second here. Okay, so let's look at example parameters. So k is equal to 1. We're going to have 1 server. Okay, so we'll start simple. And then let's suppose that the inter-arrival times are given by these numbers, and our service times are given by these numbers. So the first guy is going to show up at time 2.1. The next one is going to show up at time 1.4 later. And then the third one's going to show up at 3.5 times after that. The first service time is going to be 2.2, and then the second is going to be 1.3. And at this point, you might be asking, well, what are those? Are those seconds, milliseconds, hours, minutes? What? The answer is that at this point, it's unspecified. The only requirement is that these 2 times be in the same units,
Arnie, this was kind of confusing me yesterday. I can grasp it when it's a small thing like we're doing here. Like you just give it 5 different customers showing up at different times. But for a discrete simulation to be effective, like how do we assign how long it takes to serve somebody? Is that based on historical, or we're just making an estimate, or we can randomly create that based on some parameters?
Well, that's a great question. So you're asking where do these numbers come from?
Sort of, yes.
Yeah, so I mean in this particular case, K is very easy to come by. We just kind of look at we look at it and we say we have 5 servers. Okay, that's easy. What about these other ones where, in practice, and we're not going to address that here. Here in this class, we're going to be focusing on creating the model because that's going to be challenging enough. Where do these numbers come from? Ideally, we have some data. So if I'm consulting with the bank, for example, and they're interested in this kind of thing, then one of the things that I can do is just look at the times at which the customers kind of show up. The easiest way to do that is just sort of get some guy and stand outside the door and just sort of make a record of every time somebody shows up. In many of the systems, like a lot of times you'll have somebody be logging stuff. So when something happens, they'll be sort of typing a log into it. And so given all those numbers, there are actually several possibilities. One is we sometimes use what's called a trace simulation. That is, we take the actual numbers that were done and we run that through the simulation. That might be where these numbers come from. What we'll be doing here is we'll be just modeling this using random variables. Okay, so it's a great question. It's unfortunately in the scope of this class, we don't have time to delve into that because the methodology, the techniques we need are statistical data fitting. Okay, does that answer your question?
It does. There's
I mean,
a few gaps, but for the most part, for this, I think I got it.
Yeah. So I mean, again, for this class, we're just going to assume that these are going to be given to us. In actuality, we're going to have to create them. Now, because we're doing it by hand, and as you'll see, when doing it by hand is going to take a little while, we are going to, we're just going to simulate it for 2 customers. That's all the data we basically have. Okay, so when we get to running it on the computer, we will have there's another stop. We'll say stop it after 1,000 hours or 1,000 years or whatever. Okay, so now in the slides I have I'm going to make my doppelganger a co-host so he can share his screen. Okay, now what again, just for these purposes, and this is something that I'm going to ask you to more or less emulate for your first assignment. Okay, we're going to have like a tableau, and in the tableau we're going to have our, oops, I need the right pen. Okay, so I'm going to have the current time, the current event. Let me make this a little nicer. Come on, why aren't you writing? And then we're going to keep track of our state variables, Q, S, and L. But most importantly, we're going to keep track of the event list. Okay. So now this is the way things will always begin. So in the current time, basically before things start, everything is undefined except for the run event. Okay, so you always start with this. So nothing is really defined yet. The states are not defined. There's no current event or current time, but the event list has a run event scheduled at time 0. And the thing, and this is basically, I'm going to draw a line here that says this is where we're at. Now the event list logic that we talked about is to take the early advance time to the earliest scheduled event. Okay, what's the earliest scheduled event? It's the run event. So that now becomes our current event. And then we perform our state transition. So what is the state transition for the run event? You can check that. It was to initialize, set Q equal to 0, set S equal to K. Remember, K is equal to 1. So we set S equal to K. And remember, L is equal to Q plus K minus S. So L would be Q 0 plus 1 minus 1, and that's 0. So that matches our intuition. Nothing has quite happened yet. But now, okay, so now remember our T sub A's. We have our first one was, what was it? It was 2.1. And our second one was 1.4. That's actually all we're going to need here. Okay. So after we have performed our state transitions, we schedule any events that the run event has. Now, what is the run event schedule? It schedules an arrival with a delay of time 2.1. So now we have a single event on the event list. And that 2.1 is 0 plus 2.1. And now we're basically done. And we have used up this first time. Okay, so that's one iteration. All right, so now we move to the next iteration. What is the rule? We take the earliest scheduled event, that's 2.1. That's the arrival event. We perform the state transition. What is the state transition? It sets Q equal to Q plus 1 and does nothing else. So now Q is equal to 1, S is equal to 1, and now L, which is 1 plus 1, I'm sorry, 1 plus 1 minus 1, which is 1. Okay, and there's 1 in the system. So, okay, so we perform the state transition. Now we schedule the events. There are two things that we could schedule. Let's check the first one. If S is bigger than 0, we schedule a start service with a 0 delay. Is S bigger than 0? Well, last I checked, 1 is bigger than 0. So we schedule a start service. Okay, that's one schedule. The other that we schedule is we schedule an arrival event at now plus the next delay. What's the next delay? 1.4. So at time 1.4 plus 2.1, we schedule the next arrival. All right, and that's all we've done. That's all it does. That's it. And I'm drawing these lines to emphasize the fact that you will be tempted. You will be tempted to do more than the events are telling you to. So don't be tempted by that. Just, in fact, don't think so much. In other words, just strictly follow what the events are saying and not what you think that they're going to do. In other words, that first guy to show up, you knew he was going to go right into service, but don't do that. Just strictly follow what the event says. Okay, so turn the crank again. Okay, now we have a choice. We have two events on the event list, and they're scheduled. One is scheduled at time 2.1 and one is scheduled at time 3.5. So we pick the smaller one. We advance time to the next scheduled event. In this case, it's just, there's no time to advance, but okay, but a 0 delay is legal. And what's its state transition? Its state transition is to decrease Q by 1, so it goes to 0, and decrease S to 1, so it goes to 0. Now, what's the value of L? L is 0 plus 1 minus 0, so it's still 1. Now, what does start service do? It schedules an end service. And what was the end service? The T sub S was 2.2, and then the next one was 1.3. So the service time, the next service time is 2.2. So 2.2 plus 2.1 is what? 4.3. Okay, now we have, remember, we have removed start service, but we have not removed arrival. So that is still there. So a very important thing is to only remove, when we remove an event, we just remove one, that's it. We don't, the rules are very strict. And so events can't just magically appear and disappear. They can only appear when they're scheduled. They can only disappear when they actually occur. Okay, so now again, let's turn the crank one more time. Now we have a choice here. Now notice that I put these in not in sorted order, and for the hand simulation, that's okay. You don't have to keep them in sorted order, but you have to process them in sorted order. In other words, when I say, okay, what's the next event to occur, it can't be the end service because that's bigger. It has to be the smaller of them. So the next one is going to be at time 3.5, we're going to have another arrival. And what does arrival do? It increases our Q by 1. It doesn't do anything to S. L is now 1 plus 1 minus 0, which is 2. Okay, that sounds about right. Now we do the scheduling. First, an arrival event will schedule a start service event if S is bigger than 0. Is S bigger than 0? Not last I checked. So we don't do anything. Now something you may be thinking that is not entirely correct. We don't sit around waiting for that start service to happen. We don't do anything. It just there. Okay, now there's a good question in the chat. Do you have to draw the red lines for the assignments? No. In fact, don't. I'm drawing the red lines to emphasize how this works. Okay, so when you do it, you can, for your assignment, do it without the red lines. Okay, so I've run out of room here, so I'm gonna need to go to the next page here. But wait, let's go back. Oh yeah, okay, so 3.5 arrival. Yeah, we need to finish this. So the arrival event is, okay, we still have the end service event on the event list. The next arrival was a whole lot later. So actually for this case, I'm gonna kind of skip it. Okay, and in the assignment, I think you're gonna run out of times, and when you run out of times, you can just kind of skip them. So that's just for the sake of doing this by hand. Okay. And now, okay, so we had turn this. Okay, so what we have is 4.3 end service. So we have 4.3 end service. Okay, remember, okay, we had Q, S, and L. Now, end service doesn't do anything to Q. It was 1, and so it stays there. End service simply increments S. S was 0, now it's 1. L is Q plus K minus, remember it's Q plus K minus S. That's L. And so 1 plus 1 minus 1 is back to 1. And now an end service will schedule a start service if Q is bigger than 0. Is Q bigger than 0? Last I checked, 1 is still bigger than 0. It hasn't changed since we last did it. And so at time 4.3, we're going to schedule another start service. And then we're kind of done there. And again, you don't have to draw these green lines. I'm drawing the green lines to emphasize this is a strict iterative algorithm. So these green lines are after each turn of the crank. So again, the last thing we want to do here is, or not the last, we have a start service. Again, it decreases this, L is still 1, and it schedules an end service with a delay of 1.3. So 1.3 plus 4.3 is 5.6. And then finally, we have okay, what does an end service do? It increments S. L is now 0. And then at this point, because we ran out of arrivals, the event list is now empty. And so the event list is empty, we're done. Okay, and I did that by hand to kind of show you how you should be doing this. And the part of the purpose of this is to understand what the computer is doing. And see, the thing is that, remember I said you don't want to do so much thinking. The reason for that is because we ultimately need to implement this on the computer. If I have to do a lot of thinking, a lot of higher mental processing in order to make this work, there is 0 chance of getting this to work on the computer. Okay, John, I see you have your hand up. Question?
Yes, sir. So I see the stopping rule is to simulate for 2 customers completing service, but we've got in T sub A, a 3rd customer. In the slides, you do have their arrival. And I understand the simulation would stop before they would get served, but for our assignments, do we still need to add that arrival to the event list, but not execute?
I forget in the assignment. In the assignment, I simply say something to the effect of assume the next arrival is after that. Okay, good question. Thanks. Okay, so we basically this is, you know, to just, this is everything that we just did by hand. Yeah, in the slides, I listed what, yeah, see, when this arrival happened, I put it here. And then at this point, when we had the at this point, we had the end service, and so then we can say it was all done. It's kind of up to you. When we actually run these, we will, stopping after a certain number of events is one of the standard ways of stopping. When we start doing it on the computer, we'll actually do something like stop at a certain time. And when we stop at a certain time, there are always going to be some events left over on the event list, and then they just go away. So, but the purpose of all this is to, if we look at the values of, in fact, if we look at the whole, let's look at Q and S and L. This is our state transition. So if we were to graph this, which I didn't do, let's sort of keep it. So if we were to graph this, then we would have our state transitions. We have a time and a value for each one of them. Now, the next step of this is what we're going to do in the next class, which is going to be immediately after this one. But what I'd like to do is actually take a short break right now. I have 10:42, so if we could come back at about 10:52 or so, then we'll continue with the next class, which will be class number 3. So let's take a break.